Hello, everyone. Today we'll discuss and we'll look into a continuous beam that we can solve with a very simple method using matrix analysis. As you can see, the problem we have today is a three span. First span is 35 feet, second is 42 feet, third is 35 feet, and it's loaded on spans 1 and 2, as you can see, with uniform loads equals 0.64 kips per foot, and concentrated loads with 32 kips and 8 kips. And this load is 21 foot from the left support. This one is 16. And the distance between these two loads is 14 feet. We can summarize our input for the nodes and the elements as you can see in here. And this sometimes is useful when you use programs or software to solve your bigger structures. The first basic step of this method is to take each span and separate it from the others and assume that I have a fixed span, as you can see. Then I'll calculate for each span the fixed end moments and the reactions due to the applied loads. The fixed end moments we can get from any structure analysis book or reference. And some of the famous cases is when you have uniform load on the full length of the span like this, then the fixed end moments are WL squared over 12 on both sides, and then we'll adopt that notion that counterclockwise will be a positive fixed end moment. And the reactions, of course, for this case is WL over 2. Another case here is when you have a concentrated load as a distance A, then the fixed end moments will be given by these values, as you can see. For more details about the fixed end moments, you can consult some graph like this one, which gives you different cases and different supporting conditions when you have a fixed case, or similar to what we have actually today with a fixed hinge support. In that case, we have WL squared over 8 for this case. And for this one, we have this amount for the moment on one side. I can build my tree like this. For each load, I'll just have where that load is. And then I'll calculate the fixed end moments. And I'll calculate the reactions. And for this particular case, I used concentrated loads and one uniform load. Once you have the fixed end moments for each load case, as you can see here, you sum them up. So this basically is the summation of all these fixed end moments that we have in here. And also the reactions will be the summation of all these reactions that I have. If you want to actually expand this, and instead of that picture, you can summarize your loads into a table similar to this one. This for a uniform load. And as you can see here, you can add as much as 5 distributed loads if you would like to. And you can expand it also if you want more than these loads acting on one span. So you can tabulate the same thing as the information given in here. But the idea is the same. At the very end, for whatever uniform loads and concentrated loads, you'll sum up the total fixed end moments for that span and the total reactions. So that's step number 1. The solution itself is very simple and very easy. So basically, I just want you to know this local small stiffness matrix of each element. And the values for that 2 by 2 matrix is very simple. For E I over L. E is the Young's modulus, I is the inertia of the beam, and L is the length of the span. So I have the information here. In that case, I have uniform inertia for all spans, and I have the length of those spans given as 35, 42, and 35. So basically, I just evaluate for each span these coefficients and put them in this 2 by 2 matrix, as you can see. So basically, if you look at one of those uh, values, that would be EI over L times 4, as you can see up here. I repeat the same thing for span number 2 and for span number 3. And this method, you right away can see that you can have a different inertia per span, and you can also maybe have, for some reason or another, a different kind of modulus of elasticity, and so forth. Once I establish those local stiffnesses for each element, or for each span, I want to combine all of them into one global stiffness matrix that represent the full stiffness of the structure. Basically, I'm solving an equation which says that the stiffness matrix of the system multiplied by the unknown rotations at the supports will equal the forces or moments acting on that system. How do I establish this stiffness matrix? Basically, I'll see the connectivity between the different nodes. I have 4 nodes, and that would be the size of the stiffness, global stiffness matrix I have. If you have 4 spans connecting 5 nodes, then your stiffness matrix will be 5 by 5. So in our case, we have the 4 by 4. Element 1, as we established in the beginning up top here, connects node 1 and 2. Element 2 connects 2 and 3. And element 3 connects nodes 3 and 4. And you can see that node 2 actually is working with 2 spans, span 1 and span 2. Also node 3 working with span 2 and span 3. And that will affect our stiffness matrix as we'll describe now. For the first element, basically I take all these coefficients and I place them in here. So basically this item is simply this value, this is this value, and this one is that value. This 2 and 2 is a bit different. Why? Because as I said, it connects spans 1 and 2. So basically it will have a contribution from this part of span 1 and this part from span 2. Notice here that I took the bottom part because node 2 was the end of element 1 or span 1, and node 2 was the first for span 2. So if you can see it with that tracing, you see that this is my stiffness coefficient. Similarly, I can establish the rest of the stiffnesses. This one basically will be this value here. This one will be this value. And this last one will follow the same logic, that it's actually part of the end of span 2 at node 3 and the beginning of span 3 at node 3 as well. So these are the summation of it. And the rest of those coefficients basically are similar to what we had before, equal to those, the rest of the values. You can notice sometimes, for my own convenience, it is not for everyone can adopt the same idea. I have my cells which are green, which is a simple equal. I have red for anything that's formula, and blue basically for constants. Why this one is 0? Because there's no connection between nodes 1 and 3. So there's no interaction between the 2 nodes. And that's why this value of the stiffness matrix equal to 0. It's very simple now to get the unknowns. So those unknowns, the rotations, will equal the inverse of this matrix multiplied by the fixed end moments that are established in here. These fixed end moments, if we trace them back, we'll see that this one is coming from this summation in here. This one would be the summation of these two, this one at the end of the span plus this one, and notice the negative and positive signs because I adopt this notion for my fixed end moments. Someone can assume a different uh, notion for what's positive and what's negative, but then you need to be consistent and to remember that we're looking at loads that working on the members or loads from working on the nodes. So once we have that, then I'll get the inverse of this matrix. The inverse is very simple to do in Excel. Basically, I have to highlight this block, which is the same size of the original matrix, 4 by 4. And what I need to do is to ask Excel to calculate the inverse. So I say calculate the inverse. I can double click here. For this matrix, I close this like this. And the trick for Excel is that you have to push 3 keys to get the inverse. So it's Control, Shift, Enter at the same time. So this would be the inverse of that matrix multiplied by this vector of those fixed end moments, and that will give me the display, the rotations at the nodes. Again, to get this value, I highlight it, and then I can say, similarly, let's do it up here, equal multiplication of this stiffness matrix, inverse of the stiffness matrix, time this matrix. I close this and then Control, Shift, Enter, I get my rotations. Once I have the rotations, then I go back and for each element, I can calculate the acting in the moments globally for the whole system. So basically, I just copy or relate that stiffness matrix of element 1, which is right here. And these are the rotations at theta 1 and theta 2, as you can see. Again, I multiply this, I get this action, which is the moments due to this rotations. And don't forget again to add those fixed end moments at the elements, which are coming from here. And once I do that, I get a final moment, which is 0 at the beginning of this support, and that moment, which will be the summation of this minus this, which will give me 346. Again, if you start with a different notion for the signs, then you might add these moments rather than having the difference. But according to my assumption, the total moment will be the difference between this minus this moment. Gives me a negative of 346.76 acting on this guy in here. I repeat the same thing for the two spans. This is the stiffness for element 2. This is the stiffness for element 3, multiplied by the displacement I got from here. And for this one, I got from there. And again, I get the moments. And of course, this one and this one will be equal, but it was opposite direction, similar to this one and that one. Now, once I have this moment, then I can go back and calculate basically what are the reactions at each point. So first I get the reactions that originally calculated when I assumed it's a fixed span, and then I add the effect of the new forces that I got. If you have a moment going this way, which equals 346.76, then that will create two equal and opposite reactions and reversing that direction. So this one will be positive and this one will be negative, and both of them have the value of 346.76 over the span 35. Then I add, or I sum these two loads, I get the reaction at the first node and I get the reaction at the second node. Similarly, for the span number two, I end up with two moments. So these first are the reactions that I got first from the fixed evaluation in the very beginning. Then for this moment, which is 133, I get a 3.19 and minus 3.19. For this one, I get 8.26, and now this one is going up and this one going down according to this moment, which is the 346. I add them up, and these are my uh, reactions at those points. And similarly for the end, this one also, I had zeros to start with because that span wasn't loaded with any kind of loads. And then that moment will produce a 3.82 and the minus 3.82. I summed them up as well. The full reaction at the support, this one will be the 14. At node 2, I sum this reaction plus this reaction gives me 80. And for span 3, node 3, this plus this gives me the 30. And the last one is a negative 1, which equal to like this. So if I can sum in that graph, as you can see in here. Once I have those end moments, then I can go back and basically draw these straight lines connecting these moments that I got. And then I start hanging the forces due to the concentrated load and due to the parabola. So basically I did it for you here for the first span. These are the moments due to this negative moment, or if you consider it positive like this, then basically that's a straight line, and then just by proportional every 10th point I get a value. I plot this guy. Then for this one, that's the moment due to the parabola, which is WL squared over 8 at the middle, right here. And this one is due to the concentrated load, which was at 21 foot from the side of the span. I add them up, and then this is my final shape. You can do the same thing by knowing the moments at this point and this point. You can interpolate, get the ordinates for this span, and then you also calculate due to the uniform load and the concentrated load. So that's a little exercise that you can finalize as well. Why this method is really simple and easy to do? Because now look at, if we change any parameter, now you build it up and you connected all the elements that you have. Simply, if I want to say get rid of this load, which is the 32 kips, if I have zero load, then the spreadsheet will, because it's built that way, it will automatically adjust and calculate a new setup of moments. And then you can see that shape of the bending moment as well at the end was modified because all the contribution due to that concentrated load was eliminated. So this is a very simple method that we can adopt to solve continuous beams. And it's not bounded by any type of loads, because basically you can create that table, and for any type of the fixed end moments and the loads that you might have in here, you can build them into that spreadsheet, and then you can solve. You can extend it also to include more spans, like 4 spans, 5 spans. And remember, the size of this stiffness matrix will be always the number of spans plus 1. So if you have 5 nodes, it will be 5 by 5. If you have 5 spans, 6 nodes, then you'll have it 6 by 6, and so forth. But it gives you a very simple and easy way to solve continuous beams once you build this spreadsheet once, you can use it as many times as you want or as needed. Or if you have an error, you can just simply go back and fix it by changing maybe a few cells that are there. Hopefully, we can continue this uh, in some coming videos, and I'll show you what if you have a cantilever on one side of these spans, or if you have a fixed end rather than a support. What if you have, like, say, support settlement at one of those uh, supports, and so forth. But the essence of the method will be the same, and basically will do the same thing. I hope this will be of benefit to anyone who's solving continuous beams. And until next time, I wish you well.